You probably know about the Platonic solids. The tetrahedron, cube, octahedron, dodecahedron, and icosahedron are the only 5 polyhedra that satisfy the following 3 properties. 1. Every face is a regular polygon. 2. Every face is identical. And 3. Every corner is identical. But did you know the 5 Platonic solids are a subset of a larger set of 18 polyhedra? The remaining 13 are called the Archimedean solids, and they only satisfy properties 1 and 3. In this video, we're going to look at where they come from, as well as the related 13 Catalan solids and 92 Johnson solids. But first, we need to talk about prisms. You can make a prism from any regular polygon by duplicating it and connecting them with squares. You can do a similar thing with triangles to get an antiprism. These technically meet the requirements, but they're conventionally excluded from the Archimedean solids since they're both infinite families. Also conventionally excluded are polyhedra with self-intersecting faces, and for the purposes of this video, they won't be considered. In my opinion, the coolest thing about Archimedean solids is that they're physical objects that can be made in real life, and that just doesn't apply with self-intersecting faces. Aside from those infinite families, there are only 13. So how do we discover all of them? Well, the Platonic solids are a great place to start. Given any polyhedron, you can find the set of all reflections and rotations that leave it looking the same before and after. These, along with the binary operation of simply doing one after the other, form a symmetry group. Even though there are 5 of them, the Platonic solids only have 3 symmetry groups, since the cube and octahedron have the same one, as do the icosahedron and dodecahedron. The Archimedean solids actually have these exact same symmetries, with the exception that 2 of them can't be flipped. So if we can modify the Platonic solids in a way that doesn't change the symmetries, it might be possible to form the Archimedean solids. One operation like this is truncation, also known as corner cutting. For each corner, you make a planar cut perpendicular to the direction it points in. This turns the corner into a new face with the same number of sides as the number of faces at the corner. Meanwhile, the original faces double in edge count. If you truncate a Platonic solid, the new faces are automatically regular polygons. As for the old faces, you can make them regular by truncating a very specific amount. Truncating the 5 Platonic solids is how we get our first 5 Archimedean solids. The truncated tetrahedron has hexagons and triangles. The truncated cube has octagons and triangles. The truncated octahedron has hexagons and squares. The truncated dodecahedron has decagons and triangles. And the truncated icosahedron has hexagons and pentagons. This one in particular is so round that if you make it from a slightly flexible surface, it can basically become a sphere. Anyway, there's actually more we can do with the Platonic solids. It's possible to truncate by so much that the original edges disappear. This way, the original faces retain their edge count. This operation has a special name. It's called rectification. The rectified cube has squares and triangles, but it usually goes by the name cube octahedron. That's because you get the exact same thing if you rectify the octahedron. This is no coincidence, but I'm going to cover the reasoning a bit later. For now, let's keep going. The icosahedron and dodecahedron also produce the same thing. The icosahedron, spelled with an I for some reason, is made of triangles and pentagons. Finally, the rectified tetrahedron is just an octahedron. So even though truncation gave us 5 Archimedean solids, rectification only gave us 2. But these 2 are key to finding the remaining 6. You may have noticed that the other ones each have 2 different types of edges. For example, the truncated cube has octagon to triangle and octagon to octagon. If you take these and truncate again, these will turn into 2 different types of corners, which results in a non-Archimedean solid. But the cube octahedron and icosahedron only have 1 type of edge each, so we can freely truncate and rectify them to get 4 new solids with 1 type of corner each. But there's still an issue. Let's look at the cube octahedron, for example. When you rectify it, the new faces aren't regular polygons. Instead, they're rectangles. In order to get a true Archimedean solid, we have to rebuild it from the ground up with squares. This works, but it's technically not the same thing as before, so we have to call it by a different name. And the same thing applies to all 4. The rhombic cube octahedron has triangles and 2 different sets of squares. Some of them only border 2 squares, while some border 4. The rhomboicosahedron has triangles, squares, and pentagons. This one is actually my favorite Archimedean solid because of all the shapes involved. The great rhomboicosahedron has squares, hexagons, and decagons. It's the biggest Archimedean solid by number of edges, number of corners, and volume. And then the great rhombic-cube octahedron has squares, hexagons, and octagons. There's actually a pretty interesting property about this one. Half of the corners have octagon, hexagon, square going clockwise, and half of them have that sequence anti-clockwise. But if there are two different types of corners, doesn't this violate the Archimedean requirement that every corner must be identical? Well, the technical mathematical definition is slightly different. It requires that the polyhedron is vertex transitive, which means that any vertex can be mapped to any other vertex in a way that leaves the polyhedron the same as before. Reflections are included in this definition, which is how we can go from one type of corner to the other. Having two different types of corners lets us do something called half truncation, where we only truncate one type. More accurately, it's half rectification. The triangles aren't equilateral, but we can rebuild it with equilateral triangles to get the snub cube. It has 6 faces like a cube and 2 different sets of triangles. The snub cube is chiral, which means the mirror image is not the same thing. Depending on which corner type you choose for half truncation, you get different versions, or chiralities, but it's still only counted as a single Archimedean solid. The only other one we can half truncate is the great rhombocosa dodecahedron. This results in our 13th and final Archimedean solid, the snub dodecahedron. It's the biggest one by number of faces. It also has the highest sphericity, which measures how round it is using surface area and volume. If a sphere is 1, the snub dodecahedron is 0.98. With that, we found all 13, but there's another polyhedron that's sometimes considered a 14th Archimedean solid. If you take the rhombic-cube octahedron, cut off the top section, and put it back rotated 45 degrees, you get the pseudo-rhombic-cube octahedron. Every corner looks the same, 3 squares and a triangle, but if you look closely, there are now 3 different types of squares. 2 of them border 4 squares, 8 of them border 3 squares, and 8 of them border 2 squares. Color coding the different types, you can see that some corners have 2 oranges and a yellow, but some have 2 yellows and a green. If you try to map a corner onto one of a different type, then the corner is preserved, but not the rest of the polyhedron. So although it is locally vertex uniform, it's not vertex transitive. So under that definition, there are 13 Archimedean solids. But some of them are pretty tricky to find, so how do we know there aren't any more? Well, I came up with a pretty simple way to prove it, but if you just want to get to the Catalan solids, feel free to skip this section. So every Archimedean solid can simply be represented by which shapes meet at a corner. For example, every corner on the truncated tetrahedron has 1 triangle and 2 hexagons, so we can represent it as 663. The rhombic-cube octahedron has 3 squares and a triangle at each corner, so it's 3, 4, 4, 4. So to discover all possible Archimedean solids, we just have to find all possible configurations we can make using only regular polygons. And to do that, we need to know the interior angle for any given n-sided regular polygon. There's a useful theorem for this. The exterior angles, which are just 180 minus the interior ones, always add up to 360 degrees. So we just have to divide 360 by n and subtract from 180. With this formula, we can see that triangles are 60 degrees, squares are 90, pentagons are 108, hexagons are 120, and so on. For any configuration, if the angles add up to less than 360, it's a potential new solid. If they add up to exactly 360, then we get an infinite tiling, and anything more than 360 requires hyperbolic geometry. These tilings are interesting in their own right, and will probably get their own video, but for now we're only concerned with solids. You need at least 3 shapes to form a 3-dimensional corner, so we'll start with that. There are 3 cases. You can have all 3 the same shape, 2 the same and 1 different, or all 3 different. With all 3 the same, 3, 3, 3 is a tetrahedron, 4, 4, 4 is a cube, and 5, 5, 5 is a dodecahedron. Hexagons form a tiling, and there's nothing past that. With 2 the same and 1 different, there's another requirement. If it takes the form AAB, then A must be even. We know this because otherwise it leads to an impossible scenario. Every corner has to look like this, so you can start with 1 and then fill in the rest. Surrounding this A-sided shape must be A and B in an alternating pattern. But if A is odd, you'll eventually get a case like this, where neither shape can go there because both cases would make an illegal corner. Starting with squares, the third shape can be anything, and it's not an issue because this is just the infinite family of prisms. With hexagons, 663 is the truncated tetrahedron, 664 is the truncated octahedron, and 665 is the truncated icosahedron. With octagons, 883 is the truncated cube, and that's it. With decagons, 1010-3 is the truncated dodecahedron, and that's it. Finally, there's all three different. This category has an even more strict requirement. All three must be even. The reasoning is basically the same as before. One of them must be surrounded by the other two in an alternating pattern. So if any one is odd, you'll get a no-win situation. 468 is the great rhombic-cube octahedron, 4610 is the great rhombic-dodecahedron, and actually that's it. Now onto four shapes meeting at a corner. This time there are 5 categories. You can have all 4 the same, only 3 the same, 2 each of 2 types, 2 of 1 type and 1 each of 2 more types, and all 4 different. With all 4 the same, 3333 is the octahedron, and that's it. With 3 the same, you can use triangles, and the 4th shape can be anything, because this is the infinite family of antiprisms. With squares, there's 4443, which is the rhombic-cube octahedron, and nothing else works. With 2 each of 2 shapes, 3344 is the cube octahedron, although it's more accurately described as 3434. Trying the other way doesn't work because it leads to a no-win scenario. Then 3535 is the icosahedron, and that's it. With 2 of 1 type and 1 each of 2 types, the double shape can't be a triangle because both configurations lead to an impossible scenario. This leaves us with the only option 4345, which is the rhombic-dodecahedron. Finally, having 4 shapes all different, the smallest one possible is 3456, but even that is over 360 degrees. Now onto 5 shapes at a corner. Instead of using categories, it's pretty clear to see the only possibilities are 5 triangles, which is the icosahedron, 4 triangles and a square, which is the snub cube, and 4 triangles and a pentagon, which is a snub dodecahedron. With 6 shapes at a corner, the absolute smallest is 6 triangles, which is a tiling, so with that we're done. We've not only proven that we have all the Archimedean solids, but also that the prisms and antiprisms are the only infinite families of vertex-transitive polyhedra. Now let's go back to a mystery from earlier. The cube and octahedron both produce the same thing after rectification. Why is this? Well, they do have the same symmetry group, but they're even more closely related than that. As a fan of Platonic solids my whole life, I quickly noticed an interesting fact. The cube has 6 faces, 12 edges, and 8 corners, while the octahedron has 8 faces, 12 edges, and 6 corners. Furthermore, the cube's corners have 3 4-sided shapes, while the octahedrons have 4 3-sided shapes. This is because the 2 polyhedra are duals. To make a dual polyhedron, you basically make a point at every face and connect them in the same way as the old faces. This replaces the faces with corners and corners with faces. The edges don't change because each edge is connected to 2 corners and 2 faces. In fact, you can overlay the 2 polyhedra to get a compound with the edges lined up. Rectification turns corners into faces while still keeping the old ones, so any 2 dual polyhedra become the same thing with rectification. The icosahedron and dodecahedron are also duals, so this explains the icosahedron. As for the tetrahedron, it's actually its own dual polyhedron, so when you rectify it, all you get are triangles, and they form an octahedron. Although an interesting side note, if you distinguish the 2 types of faces with different colors, it's called the tetrahedron. When you truncate it, you get 2 different types of corners, and with that, you can use half rectification to get the snub tetrahedron, which is just an icosahedron. So taking the dual of a Platonic solid gives you another one. You might expect this to also be true about the Archimedean solids, but as it turns out, their duals are a completely different set called the Catalan solids. Since dual polyhedra switch faces and corners, each property from the Archimedean solids carries over in a different form. Instead of being vertex-transitive, the Catalan solids are face-transitive, and instead of each edge being the same length, now each edge has the same dihedral angle between the faces. But the coolest part is that there's also a dual version of truncation, which we can use to construct them. Instead of turning each corner into a new face, we turn each face into a new corner by adding a point in the middle, connecting it to the corners, and raising it up a bit. It actually has different names depending on the shape, and we can apply this to the Platonic solids to get 5 Catalan solids. These are the triachus tetrahedron, tetrachus cube, triachus octahedron, pentachus dodecahedron, and triachus icosahedron, all of which are made of isosceles triangles. The dual equivalent of rectification is similar. You just raise up the new point so much that two faces become coplanar and combine into a single face. The cube and octahedron again make the same thing. This is the rhombic dodecahedron. It has 12 rhombic faces. The type of rhombus is not the typical 60 and 120 degree one. Instead, the ratio between the diagonals is square root of 2. The dodecahedron and icosahedron also make the same thing, the rhombic triacontahedron, which has 30 rhombic faces. Its type of rhombus is called the golden rhombus, where the diagonal ratio is the golden ratio. These two are the duals of the cube-octahedron and icosahedron, and they retain the property of being edge-transitive. These four are the only non-Platonic solids that are edge-transitive, so I would consider them honorary Platonic solids. Anyway, the tetrahedron just becomes a cube, which makes sense since the rectified tetrahedron was just an octahedron. Now we have 7 Catalan solids, and just like before, we can take the edge-transitive ones and apply the same operations again to get 4 more. The Dysdiaphus dodecahedron comes from the rhombic dodecahedron. It has 2 different types of faces, which are scalene triangles and mirror images of each other. They look very close to being right triangles, but they're not. The deltoidal icosatetrahedron also comes from the rhombic dodecahedron. It's what you get once these pairs of faces become coplanar. Its faces are kites. The Dysdiaphus triacontahedron comes from the rhombic triacontahedron and also has 2 types of scalene triangle faces. And the deltoidal hexacontahedron also comes from the rhombic triacontahedron and it has kite faces. Now the only ones left are the duals of the snub cube and snub dodecahedron. Unsurprisingly, we can get them through half triachus. The pentagonal icosatetrahedron comes from applying this to the Dysdiaphus dodecahedron. Just like the snub cube, it's chiral with different chirality depending on your choice of face type. Finally, the pentagonal hexacontahedron comes from applying this to the Dysdiaphus triacontahedron. It's also chiral. Now, you might also remember the snub tetrahedron, aka icosahedron, which came from distinguishing faces of the rectified tetrahedron, then using truncation and half rectification. Well, the dual of the truncated octahedron is the tetrachus cube, and we can color code the faces to then do half triachus and get the one and only dodecahedron. But the Dysdiaphus triacontahedron is actually my favorite Catalan solid because it really shows icosahedral symmetry. All of these great circles represent reflection planes. Also, you can see so many other Platonic and Catalan solids within it. There's the icosahedron, triachus icosahedron, dodecahedron, pentachus dodecahedron, rhombic triacontahedron, and deltoidal hexacontahedron. Now the Catalan solids are defined as the duals of the Archimedean solids, so there are only 13 of them by definition. But there are more polyhedra with the same properties. The duals of the prisms form another infinite family, the bipyramids. Likewise, the duals of the antiprisms form an infinite family called the trapezohedra. We've seen how the octahedron is just a triangular antiprism, but it's also a square bipyramid. And the cube is also a square prism and a triangular trapezohedron. Finally, the pseudo-rhombicube octahedron has a dual called the pseudo-deltoidal icosatetrahedron, where every face is the same shape, but it's not face transitive. You can get it by twisting half of the solid 45 degrees. So by removing one requirement from the Platonic solids, we went from 5 to 18 plus 2 infinite families. But what if we took things a step further and removed 2 requirements? How many polyhedra can you make using only regular polygons? Well, the answer is infinitely many, and it's not even easy to categorize them. For example, you can make all of these just with triangles. But we can disqualify these by adding one small condition. A convex set has the requirement that for any 2 points in it, the line connecting them is completely within the set. If we require the polyhedra to be convex, then any edge with a dihedral angle over 180 will violate this condition. This keeps things to a reasonable 110 plus 2 infinite families. These are the Platonic solids, Archimedean solids, prisms, antiprisms, and 92 more known as the Johnson solids. The rest of this video will be dedicated to finding all of them. But don't worry, it's actually pretty simple. The vast majority can be made by simple cut and paste operations on the vertex transitive ones. When you join 2 polyhedra together along a common face, their dihedral angles add, so we have to make sure they add up to less than 180. But how do we know the dihedral angles in the first place? Well, there's actually a pretty simple formula. If 3 angles, A, B, and C, meet at a corner, then the dihedral angle between A and B is arc cosine of cosine C minus cosine A cosine B divided by sine A sine B. For example, on the great rhombic-cube octahedron, the angle between the square and hexagon ends up being 144.7. Predictably, the dihedral angle on a cube is 90 degrees, and between two squares of a prism is just the internal angle of the base. And if you have more than 3 shapes meet at a corner, you can usually cut off some of them to make it 3. To make sure the dihedral angle sum is less than 180, you need at least one of them to be less than 90. So the best polyhedra for joining with other polyhedra will have one face with only acute dihedral angles. We'll call this the base. With a triangle, square, or pentagon, you can add triangles to get a pyramid. The triangular one is just a tetrahedron, but the others are the first 2 Johnson solids. With a hexagonal base, you can't make a pyramid because it ends up being flat. But now you have another option. You can add squares and triangles in an alternating pattern, and then a triangle on top to get the triangular cupola. You can use the same technique on an octagon or decagon to get the square cupola and pentagonal cupola. Finally, with a decagon, you can alternate between triangles and pentagons, then add 5 triangles and a pentagon to get the pentagonal rotunda. These 7 polyhedra are the only ones with the properties we want, so now it's time to start combining. For now, we'll only use prisms and antiprisms because modified Platonic and Archimedean solids will be their own category. The typical order goes type by type, but I think it makes more sense to go shape by shape. So starting with a triangle base, you can take the pyramid and attach another one to get a bipyramid. You could instead add a prism for an elongated pyramid, and then from there, you can add another pyramid to the other side of the prism. Usually you can add an antiprism and it's called gyroelongation. But with a triangular base, the dihedral angle is exactly 180, and the faces combine into a non-regular polygon. With a square base, you have the same options as before. This time, gyroelongation works, but now the bipyramid is just an octahedron. You also have the option of adding square pyramids to the side of prisms. With a triangular prism, you can do this once, twice, or 3 times. With a pentagonal prism, you can do this once or twice. And with a hexagonal prism, you can do this once, twice opposite, twice not opposite, or 3 times. There's one more thing you can do with squares. The triangular prism can be thought of as a cupola, and the square base has 2 90-degree dihedral angles and 2 less than 90, so you can actually combine 2 triangular prisms together. With a pentagonal base, you again have the same options as before, except the gyro-elongated bipyramid is just an icosahedron. Hexagons get a bit more interesting. When adding a second cupola, you have the options of aligning squares to squares or triangles to squares. This second option is just the cube octahedron, but you have these same 2 options for the elongated bicupola. You'd think there would also be 2 options for the gyro-elongated bicupola, but since the faces of an antiprism are misaligned, the 2 forms are mirror images of each other, so they're counted as a single chiral Johnson solid. With an octagonal base, you have these same options, but the elongated bicupola is interesting. If they're aligned, you get the rhombic-cube octahedron, and if not, you get the pseudo-rhombic-cube octahedron. It may not be an Archimedean solid, but it is a Johnson solid. Finally, the decagon has the most options of all. Starting with the cupola, you can add another cupola in 2 ways, a rotunda in 2 ways, a prism or an antiprism. From the antiprism, you can add a cupola or rotunda, and from the prism, you can add them in 2 different ways each. And that's not even including the ones with a rotunda but no cupola. In that case, you have the same options as before, except that the non-aligned birotunda is just the icosahedron. So by just combining these 7 with prisms and antiprisms, we have 57 Johnson solids. Now it's time for some modified Platonic and Archimedean solids. We've already seen what we can do with the tetrahedron, cube, and octahedron, since they're just special cases of things we looked at. With the dodecahedron, you can add a pentagonal pyramid to any face. You can't do this to adjacent faces, so the only options are doing this once, twice opposite, twice not opposite, or 3 times. With the icosahedron, you can cut off a pentagonal pyramid from any corner. You can do this once, twice opposite, twice not opposite, or 3 times. 2 of these are things we've seen before, but 2 of them are brand new. In fact, this one has a single face where you can add a tetrahedron for another Johnson solid. Now for the Archimedean solids. 6 of them don't have any associated Johnson solids because you can't make cuts or add anything to them. Then with 3 of them, you can cut them in twist sections, but it's nothing we haven't seen already. That leaves 4. With a truncated tetrahedron, you can add a triangular cupola to 1 hexagonal face. but the dihedral angles mean you can only do this once, and you have to align the squares to triangles. The truncated cube has a similar story. You can add a square cupola once or twice. And then with the truncated dodecahedron, you can add a pentagonal cupola once, twice opposite, twice not opposite, or 3 times. Finally, there's the rhombocosidodecahedron. You can cut off a pentagonal cupola from any side. You can also put it back twisted the other way. Combining these, there are 12 options in total. You can make a cut once, twice opposite, twice not opposite, or 3 times. You can twist once, twice opposite, twice not opposite, or 3 times. You can make a cut and twist opposite or not. You can make 2 cuts and a twist, or 2 twists and a cut. With that, we have 83 Johnson solids. The remaining 9 are considered elementary Johnson solids because they can't be made with cut and paste operations, but they are still related to some previously discussed polyhedra. First, let's look at the icosahedron. One way to think of it is as 2 opposite triangles connected by 2 layers of triangles. It's possible to extend this idea to other shapes. With squares, the snub square antiprism is basically if an icosahedron just kept on going. With pentagons, though, it's not convex. There's also the digon. It's just a line, which makes it a degenerative case, but you can still apply the same idea to get this, the snub disphenoid. Constructing the remaining 7 involves these structures called lunes, basically a square and 2 triangles. On an icosahedron, you can remove 8 triangles to get a hexagonal opening. After a bit of adjustment, you can cover it with 2 lunes for the sphenomegacorona. You could also use 3 lunes for the hebasphenomegacorona. Or you could take those 8 triangles from before and attach 2 lunes to those to get the sphenocorona. From there, you can even add on a square pyramid. You can take the hexagonal antiprism and add 2 lunes on top and 2 on the bottom for the disphenosingulum. You can take 2 triangles and 2 pentagons from a rotunda and connect 2 of these with 2 lunes to get the biluna birotunda. And finally, you can take 3 pentagons and 4 triangles from a rotunda, add 3 lunes, then 3 triangles and a hexagon for the triangular hebasphenorotunda. With that, we have all 92 Johnson solids. It is proven that this is all of them, but it involves a computer search. But we can still disqualify some going case by case. There are many polyhedra whose faces are almost regular polygons, but just barely don't work with them. These are called near-miss Johnson solids. For example, this one has 4 regular hexagons and 12 non-regular pentagons. If the faces were regular polygons, then this corner would tell us the dihedral angle here should be 131.2, but this other corner tells us it should be 116.6. This is a contradiction, so the polyhedron is impossible with regular polygons. There are other techniques, like if the angles at a corner add up to 360 or more, it's not a Johnson solid. But some of them are so close that you can make physical models of them that can withstand the discrepancy. So, throughout this video, we've discovered all 13 Archimedean solids, 13 Catalan solids, and 92 Johnson solids. Let me know in the comments your favorites from each set, as well as the kind of videos you'd like to see in the future. This video was a lot of work, so make sure to like and subscribe, as well as follow me on Twitter or Threads. Thank you for watching, and I'll see you next time. Bye!